Hello, good morning everyone. Let's start today's session. So today we are going to discuss about the wrapper methods under feature selection. We know that we are having two kinds of evaluation strategies under feature selection algorithms. Those are meant for reducing the dimensionality of the feature vectors. In the last class, we have gone through the filter methods. So today we will be covering the wrapper methods. Those are being used for feature selection. As we have seen this diagram, what wrapper methods are? Wrapper methods are supervised methods. So we are having the training data with a complete feature set. We are having some search strategies. So using these search algorithms, we are finding out the feature subsets from the original set. This feature subset is being used with respect to the machine learning algorithm under consideration. For that feature subset, we are predicting the accuracy and the process gets repeated. And we are going to find out the feature subset such that it produces the minimum error. Right, and that feature subset would be the final feature subset, and that final feature subset will be utilized for further experimentation. So this is the theme of wrapper methods. So as I stated, in wrapper methods we try to use a subset of features and train a model using that feature subset based on the inferences or based on the performance that we evaluate from the previous model. We decide whether to add or to remove the features from the existing subset of the features, and the process gets repeated. So the problem is essentially reduced to a search problem wherein we are finding out the appropriate subset of the features. These methods usually are computationally very expensive. Some of the common examples of wrapper methods are forward feature selection and backward feature selection or backward feature elimination algorithms. In forward selection, what we do is both the methods are actually the iterative methods. In forward feature selection, what we do is we start with having no features at all. So we start with empty feature subset, and in every iteration we keep on adding the feature which best improves our model till an addition of a new variable does not improve the performance of the model. So initially in feature selection method, initially our feature subset is empty, and in every iteration we go on adding one feature into this feature subset, and we test for the performance of that subset, right? And we go on repeating this process until the performance becomes stable. Meaning, if we go on adding further features, if there is no improvement in the performance of the model, then at that point we may stop. Right? In contrast, in backward feature selection, what happens is we start with all the features. So in backward feature elimination, initially our feature subset is the entire feature vector, right? And during the iterations, we go on removing the least significant features. So we go on removing least significant features in every iteration. And here in forward selection method, initially our feature subset is empty and we go on adding the most significant features in every iteration. So this is how our algorithms work. So let me give you the clear idea about the forward feature selection algorithm. So let us assume that we are having a feature set F with input dimensions n. So we are having a feature set or a feature vector F wherein we are having n number of features. So dimensionality of our feature vector is n dimensional feature vector. So we are having the features like x1, x2, x3 up to xn. So dimensionality of our feature vector, original feature set is n. Now let us denote the error associated with this feature vector f as E of f. So E of f denotes the error incurred on the validation set when only features in f are used. Right? So E of f is the error associated with the feature vector f. Here we are referring to this error, which is mean squared error in case of regression task or misclassification error in case of classification task. So with these terminologies now, let us look at the algorithm for forward feature selection. So as I stated earlier, the algorithm begins with F as the empty set. Right? So F, that is the subset that we are supposed to come up with, is initially empty. And the initial error E is initialized to some large value. Right? Now, what we do next is we go on repeating until the error decreases or until the decrease in the error is greater than some threshold. So this threshold is user defined threshold. So what we are going to do is we are having some set F. We begin with empty set and in every iteration we are going to find out the error associated with the subset of the features that we have. We are going to repeat the process until the error decreases. So initially my error may be too large, then in the next iteration my error goes on reducing. So in every iteration my error goes on decreasing, right? So we are going to repeat until my error is decreasing and it becomes almost same after some point, right? So we go on repeating till that point, or we go on repeating till decrease in the error is greater than some threshold, meaning I'll be having some threshold which is minimum value, and if the error, the difference in the error of the previous iteration and the next iteration, this difference is greater than that threshold, we are going to repeat. But if the difference in the error of two consecutive iterations becomes less than that small threshold, then we are going to stop, right? So this is the limiting criteria of our algorithm. Now we are going to repeat for all values of I. So what is this I? I is varying from 1 to the number of features that we have n, right? So we are repeating for all those n number of features, right? So repeat for all I. What we are going to repeat? We are going to train the model on training set and calculate the error with respect to the old feature set union the new feature added into the feature set, that is xi, right? And we are going to validate our model using the validation data set. So I'll repeat what I'm going to do. Initially, my feature subset is empty. I'm not having any feature, right? So in this loop, what we are going to do is I varies from 1 to n. So let us assume that I is equal to 1, right? So what we are going to do is we are going to pick the first feature, that is x1, right? Now, if I'm having m number of instances in my data set, then for all those m instances, I'll be making use of only one feature x1, right? So with the only feature x1 now, I'm going to train the model, the machine learning algorithm, right? And I'll be computing the error for the feature vector having this only feature. Earlier it was empty, so I'll be computing the error now with the empty feature set earlier union the first one x1. So I'll be computing the error for the feature vector comprising of only x1, right? And this error is being computed on the validation set. So the model is prepared by making use of my training data set, and the error is computed by making use of the validation data set, right? Now we have computed this error for this x1 first feature. Now I'll be incrementing the value of I to 2. So I'll be having now the feature x2, right? So for every feature, I'll be computing the error with that respective subset of the features, right? Now, what next? I'll choose xj such that j is equal to min I e of f union xi. What does this mean? See, we are going to add one by one all the features and we are going to compute the error, right? So we are having all the errors associated after adding the respective feature in our feature set. So which feature set we are going to select, or which feature we are going to add actually? We are going to add the feature such that the error for that feature is minimum, right? Say for example, after adding say x4 into the feature vector, if I am having minimum error, this means that I'll be selecting this j value as 4. So for fourth feature, I am having minimum error. So I'll be selecting x4, right? The fourth feature, right? And that fourth feature is being added now in my feature subset f. So old feature subset union the new feature that we have selected. And how we have selected this feature? We have computed the error of my model by adding every feature into the earlier subset, right? And we have computed all those errors. We are finding out the minimum error, and that minimum error is meant for the newly added feature. So because of addition of that new feature, we have come up with this minimum error, and that is why we are going to find out the feature. When it gets added, the error is minimum, and that feature is actually being added now, right, in my feature subset, and this process gets repeated for all the features. Is there any doubt so far? Have you understood the algorithm, or may I repeat once again? Yes. Yes. See what we are going to do. Initially, my feature vector is empty. I'll be selecting I equal to 1, meaning I'll be selecting first feature, right? I'll be finding the error with respect to this feature vector comprising of this x1. Then I'll increment the value of I to 2. I'll be having x2. I'll be computing the error with x2 and so on. So I'm having n number of features. So finally I'll be adding the last feature. I'll be computing error for the feature vector comprising of this xn. Right now, what I'm having right now is all the errors. So whenever I'll be having the individual feature, then whatever may be the error, I'm having all those errors with me. So what I'll do is I will find out the minimum error. So suppose for x4 I am having minimum error. So what it indicates? It indicates that for feature vector comprising of x4 only, I'll be having the minimum error. So I'll select this number 4, our minimum error f union xi, right? So our minimum I is now 4. So j gets assigned the value 4. So x4 is the feature that I need to add, right? So my final feature subset, earlier it was empty and it becomes now x4. So this is my final feature vector. So now in the next iteration, I am having this feature vector f as with single element x4. So in the next iteration, once again, we are going to repeat the process. So once again, I'll begin with I equal to 1, right? So my old feature vector comprises of x4. Now I will add x1 into that, right? So now in my feature vector, I'll be having two features, x1 and x4. With these two features, I'll be training the model and I'll be finding the error. Correct? Now, what next I'll do? For I equal to 2, I'll be having x2. So what I'll do? My old f is having x4 and now I'm adding x2. So I have tested with the combination x4, x1. Now I'm testing the combination x4, x2. Once again, I'll train my model with x4 and x2 and I will find out the error with validation data set. So now with every feature subset, I'll be having the error. Now once again, what I'll do is I'll find out the minimum error. And for whatever is the minimum error, whatever is the feature that I have added, that feature is now finally being added into my old feature subset f. So if this time in this iteration x2 is the feature which is producing minimum error, then I'll be having the new feature vector or feature subset as old is x4 and now x2. So in next iteration, this would be my f, and once again I'll go on repeating the process, and this process continues till my error is, or decrease in my error is greater than some threshold, right? So if at certain instance of time my error is not decreasing much, then I'll stop. And at this instance, whatever is my feature subset, that feature subset is being finalized for further experimentation, right? Any doubt? Yes? Yes? Any doubt? So I hope you must have understood what we are trying to do in forward feature selection. We are experimenting with all the features and we are trying to come up with a feature subset that gives me minimum error, right? So this is forward feature selection algorithm, which is a wrapper method. In the next algorithm, that is the backward feature selection or backward feature elimination, it is doing exactly opposite. So in backward feature selection, we start with all the features. So initially my feature vector comprises of all n features. Right? And what we do is we go on removing the least significant features at every iteration. So in every iteration, once again, the similar kind of procedure that we have seen is followed. So we go on testing individual features, right? And whichever feature is least significant, we try to remove that feature, right? That after removing this feature, it improves the performance of my model, right? Or whenever I am removing the feature, it will decrease the error associated with my feature subset. And this process goes on repeating. So we are going to repeat until there is no improvement after removing any more features, right? So this is how the backward feature selection algorithm works. To have a detailed algorithm for backward feature selection, please refer to our textbook by Tom Mitchell. So for this content, we are referring to the Tom Mitchell's book for forward feature selection and for backward feature selection algorithms. So you are advised to refer to that particular book for these algorithms, right? Also, I have uploaded a detailed discussion about the forward feature selection algorithm with example. So you may refer to that video as well, right? So I hope you must have understood these two algorithms, forward feature selection and backward feature elimination. Now, in addition to these two, we are having one more algorithm, and that is known as floating search. So the process of testing the features one by one, as we did in the forward and backward selection process, this algorithm or this process may be costly, as it requires the system to train and test n square times. So the complexity of the algorithm becomes order of n square, right? And to improve upon this time consuming process, we are having some other algorithm for searching the feature subsets, and that is the floating search. So this is the local search procedure, but this procedure will not guarantee the optimal subset, but this is comparatively faster than the earlier search processes, right? So sometimes it may happen that xi and xj, if there are two features xi and xj, sometimes it may happen that xi and xj individually by themselves may not be good, but whenever we put these features together, it may happen that these two features put together may decrease the error in our machine learning algorithm, right? So in the previous algorithms, it is not possible for us actually to add or remove simultaneously more number of features, right? But in floating search method, it is possible to add as well as remove the features at the same time, so as to come up with a good feature subset. But please remember, this floating search method will not guarantee the optimal subset. We may have near optimal subset, right? But this algorithm will work fast. Okay, so this is one more floating search algorithm that we may use. Okay, so using this floating search method, it is possible to add multiple features at a time. Multiple features can be added at a time. In the earlier algorithms, we were supposed to add only one feature at a time, right? We can track or we can backtrack and check whether the previously added features can be removed after current addition, right? So at the same time, it is possible to add more than one features, and also we can backtrack if the previously added features are not performing well, right? And as this is more flexible process of adding and removing the features, we say that it is a floating search method, right? But sometimes it may increase the complexity if more number of additions and removals are there, right? So that's all with the wrapper based methods of feature selection. So here is the summary of filter based methods and wrapper methods. So under filter methods, as I stated earlier, the filter methods are unsupervised methods. So generic set of methods which do not incorporate a specific machine learning algorithm. But wrapper methods are evaluated on a specific machine learning algorithms to find the optimal features, right? So these filter methods are unsupervised. They are not using any machine learning algorithm for evaluation. Here we are using the supervised method, right? The next difference is the filter methods are much faster compared to the wrapper methods in terms of time complexity. Whereas for wrapper methods, we require high computational time for a data set having many number of features. Filter methods are less prone to overfitting, whereas there are high chances of overfitting because it involves training of machine learning models with different combination of features. Right? So it may happen that sometimes the wrapper methods come up with the models, those are overfitting the data. Right? Now, few of the examples of filter methods are the correlation methods, chi-square test, ANOVA, information gain, and so on. So typically the filter methods are using some statistical measures like correlation coefficients, chi-square test, and so on. We have gone through the detailed discussion of these statistical measures and when to use which method, right? So filter methods are basically using the statistical measures, whereas the wrapper methods are using the algorithms like forward selection, backward elimination, floating search, stepwise selection, and so on. Right? So these are the major differences in filter methods and wrapper methods. So with this, we conclude discussion related to feature selection.